We're now going to take a look at evaluating volumes of solids of known cross-section. Now this technique is going to allow us to calculate volumes for certain geometric solids that are not generated by rotation of a region around an axis. Now there's not a single formula that we have for these problems. It all depends on each individual problem. But you'll see from the example that we look at here, there's a general technique that you can follow to solve problems like these. So let's take a look at this example. So here we want to find the volume of a pyramid having a square base with a width of 10 and a height 5. So the first thing we want to do here is draw a picture. So let's draw a picture of our pyramid. So here's a picture of our pyramid, and we want to find the volume of it. So let's take a side-on view of this pyramid. If we look from the side like this, notice that our pyramid will look something as follows. So here's a side-on view of our pyramid drawn with respect to the x and y axes. Now let's notice this. If we take this shape and we slice it up into thin rectangles, one typical rectangle would look like this, let's say. So here's one rectangle. Let's label this point right here as x comma y. Now this slice right here, over here it would actually look like this. So that's approximately what this rectangle here looks like over here in 3 dimensions. Now let's calculate the volume of this little slice right here. So the volume let's call it delta VI. Let's see, for this rectangle right over here, what is the width of it? Well, this is x right here on the x-axis, and this is y. And let's suppose that it has a thickness, call it delta y. So then the volume of this piece is going to be the area of the base of this shape here. Now the area of the base is going to be this distance, which is 2x squared, 2x times 2x, times the thickness delta y. Now what we do is we need to add all of these up and take the limit as the number of partitions here goes to infinity. So then the volume of the pyramid Alright, so here's what our volume would be. It would be this limit as n goes to infinity of the summation of 2xi squared times delta y. I should have really labeled these as x sub I and y sub I up here. Let me do that here. And then this would be xi right there, and that would be yi right there, and this would be an xi right there. Now, in the limit as n goes to infinity, this summation here turns into an integral of 2x squared dy. And now what does the y go from? Well, the y right here goes from 0 to 5. So we will integrate from 0 to 5. Now the only problem here is we have an x, we don't have a y. So what we need to do is up here we need to write x in terms of y. Well, this curve right here, if we were to find the equation of this line right here, that line has equation y equals negative x plus 5. You see the slope of this line is negative 1, so there it is, negative x, and the y-intercept is 5. So that's the equation for this line. And you see we can solve this then to find that x equals 5 minus y. So then the xi equals 5 minus yi, and we could have substituted that right in here, or we can just replace this x right here with 5 minus y. And then just moving up here, that will equal, and I should have my parentheses like this down here. And so this is going to be 10 minus 2y, the quantity squared, and then just foiling this out, we get and there you go. That's our integral and representing the volume of the pyramid, and we can easily evaluate this now. And I'll let you do that, but I'll tell you that the answer here is, so that would be the volume of this pyramid. So once again, notice the way we did this. We just partitioned this interval from 0 to 5 into little rectangles. We took one rectangle right here as an example, calculated the volume of its three-dimensional equivalent over here. So the volume we found out was 2xi squared times delta y. We summed them all up, took the limit as n goes to infinity, and turned this into an integral. And then we just replaced all the x's with x as a function of y, which came from the equation of the curve that this point was on. And then we got our integral, which we could easily evaluate because it's just an integral involving a polynomial. And there you go. So that's one way that we can evaluate solids of known cross-section. You see, this technique is referred to as known cross-section because this is called a cross-section right here of our volume, and we could easily calculate what it is here based on the geometry of the problem. Now let me just mention one shortcut that you'll see people oftentimes use with these problems. If you recall, we found that Now, taking the limit as the partition sizes goes to 0, or as the delta y here goes to 0, we get that like that. And now we can just say that the volume is the integral of the dv terms, which is the integral of this. But now you have to realize, oops, that should be an x. You have to realize that the in the original picture, remember that the y went from 0 to 5, and the x is equal to 5 minus y. And so then you just get which was exactly what we had before, like that. So in other words, the moral of the story here is once you find something like this, an equation like that, just integrate each side, and then you'll get your answer. You do have to be careful with your limits of integration, however, and if you have, for example, this x here doesn't match up with the y that we're integrating with respect to, so we have to find what x is in terms of y, and that was from the geometry of the problem.